Okay, thanks, Matt. Again, thanks for the invitation to just share some ideas that I've come up with. I'm sure there's other people in the room could do similarly, but this is a perspective of mine. Okay. So I wanted to focus on the primary geodetic aspects of SLR, which was a key point of Frank's talk just now. And it's just point out that we all know it's a major contribution, SLR is a major contribution to the realization of the ITRF. So accurate data is absolutely critical in this effort. And determination of long wavelength gravity terms in conjunction with dedicated missions. So we supply the long wavelength terms for, say, GRACE missions. So I want to just discuss which satellites and best observing strategy, primarily for the geodetic spheres, the primary geodetic spheres, and also threats from the other techniques, just to throw that out there, lest we get complacent. So the reference frame, all four techniques are working towards achieving the common GGOS goal, which again we've heard for Frank, that's not going to be relaxed. If anything, it's going to be made tougher. With accuracy 1 millimeter and stability, i.e. rates of change of coordinates at the level of 0.1 millimeters per year. That's what we're tasked to do. The laser ranging technique, in principle, is capable uniquely to determine the origin of the TRF, the centre of mass of the Earth system, and with VLBI, as we've heard this week already, the scale of the TRF. And again, other groups, other techniques are moving towards that. Just as from the ITRF 2020 results, we have SLR, XYZ, geocenter, and scale. Something happening to the scale here. When there was only one LAGEOS, very tricky task, but it's in there for long-term studies. That's still a useful, valuable early data set. But then look at Doris. X, Y, Z is always, Z is always tricky for techniques that are affected by the ionosphere. But the scale there's some drift, but it's looking pretty good. The VLBI scale, as we know, there is still, but much reduced, difference between the SLR scale and the VLBI scale. And we've done some work on, I'll get to that in a moment, but there's been a lot of work done on why there was a scale difference and why this perhaps still needs to be resolved. Okay, so as I say, intrinsically the technique is capable of 1 millimeter range accuracy. In practice, this is hard, as we all know, if we're involved with stations or analysis, or both, but it's not impossible. The key is to detect and mitigate long-term entrenched systematics, station by station, as well as detecting transitory glitches, which with the best will in the world there will always be, or making very accurate measurements. Something will have changed somewhere in the data chain, and blunders will be made. And work that we did with Jose and Zuhir Al-Tamimi, we showed that all stations, were and are found to have some systematic bias at some level. And that's from a few millimeters to a few centimeters or more. And I offer some reasons perhaps why that is the case. Target board survey error, any error in that. Very difficult actually to measure accurately the fiducial point of a big telescope, distance to the target board, time of flight hardware error, which is we're all at the mercy of errors in that, although we buy more and more expensive time of flight measurements. There are problems sometimes, and variable return rates, etc., may impact time walk of our detectors. So the ITRF 2020 strategy before producing the ITRF, or the laser ranging input into that, a great deal of work was done by the combination centres, Cinzia in particular, and ERICOS, using the ACs that were tasked with solving for range bias for all stations for the whole period, 83 to 2020. So they looked at those series of range biases that were solved along with the reference frame. So coordinates and range biases. That's going to produce a noisier solution, as I'll show, as we know, but the combination centres average those range biases over certain periods of time when they could see visually that there was no real change. And those results per station were used to populate this data handling file. Then the ACs were tasked to rerun the solutions using those averaged range bias values from the data handling file and reprocess again to form the reference frame, but not solving for range bias during this second stage. That's a statement of what actually happened. So I'll leave that out there for discussion, really. Is that the best way to do things? But most important in that scheme like that is that any bias remains fixed. And a plea really is, as I've heard for many years, that hardware practices, observing practices, are not often tuned. They're not played around with every few days or weeks. But a fixed bias from the scheme I've just discussed will be determined, and that actually doesn't matter. If you're 3 millimeters wrong, let's see that 3 millimeters shine through from the analysis and be applied. And it's essential also that site logs are modified to follow changes. Particularly important now, I say now because we have excellent centre of mass corrections for the major geodesic spheres. Those centre of mass corrections derived by Jose Rodriguez have been computed based on practices written in the site logs. Data clipping we saw today, different clipping when you make the normal points will affect the 0 point of your measurement, but the 0 point of your measurement has been used in the theory plus instrumental information in the convolution in order to determine the centre of mass corrections. So there's a closed loop there which we need to maintain. And then, given the need mostly to be solved, I would contend, together with the reference frame, we need lots of data. And it's very useful to get low elevation parts of passes. This greatly helps the separation of height and range bias, because at, say, at the zenith, range bias and height are intimately and completely correlated. You only get a separation in the partial derivatives where a range bias partial derivative is unit, 1, but the height partial derivative is a function of elevation. So they will separate if you get very low elevation. So a scheme that I think probably lots of stations are doing is particularly for the Lejos and LARAS-2, which we now have as a fantastic new target, to get as low as elevation as possible. And I would say resist quitting at low elevation to get, say, a LEO satellite, although they're important as well, of course. But I think it's probably better to continue tracking down than, unless you're absolutely sure you're going to acquire a satellite at low elevation, then you can do the low elevation part at the end of the pass when you're already acquiring it and everything's set, offsets, etc. And just finally, I think a couple of stations where we've gone off-piste and solved ourselves for range bias, and this is with Andrea, we've solved for range bias for all the stations, and as well as the coordinates, and for Yerigidi and Houseman-Sue, this is the height time series we get, which we contend is essentially unbiased, even though we know in Houseman-Sue we had problems, which Andrea talked about yesterday, with various counters that's historically been used in the system. These are slightly noisy, but we would contend they're essentially bias-free because we're doing simultaneous range bias and coordinates. So many new demands on laser ranging telescope time, and there's some fantastic talks today about relativity, which was extremely interesting. But it's important, though, to remember to support the realization of the reference frame. There's a good number of Lagios, Lares2, Echelon normal points, and those satellites are used also for J2, J3, and perhaps beyond to constrain, for example, the GRACE follow-on gravity fields, which can't determine those low-order long wavelength terms. Actually, the work we heard today about relativity addressed by the Lagios and Echelon satellites, so yet another reason to concentrate on. Remember those. And document and publicize system and practice changes. And my final point is document and publicize system practice changes. Okay, I think that's it.
Great. Thank you, Graham. Thank you very much. Any quick thoughts on or question?
Hi, Graham. Sorry. It just struck me, you're talking about maintaining a static bias, and 3mm is okay as long as we know about it. That's somewhat incompatible with what Frank was just saying about us needing to get bias-free systems that they can use the data straight off.
Yes.
Now, I know there's a proposal to use the long-term biases obtained from the geodetic work and pass those on, but that was slightly controversial. I wonder what you thought about that idea.
Yes, I guess what I'm saying is, if you think there's a bias, then sure, investigate it, sort of offline, as it were, until you're absolutely convinced. And then make a big correction, make a correction, whether it's 3mm or a centimetre, document that. Yes, don't go on having seen some results maybe that show there's a bias. I'm just saying it's not a complete disaster because we can solve for that bias if it's not played around with.
Thank you. Thank you very much. Thank you.